So we'll start off with oxidation states, and we'll look into redox reactions. And so this is just a bit of an overview of what our redox reactions are. So essentially, redox is a type of reaction. So you can consider, like, you've got your addition reactions, your decomposition reactions, your combustion reactions, your single displacement, double displacement. You've got all those types of reactions. Redox is just another one of those types of reactions. And so essentially where the word redox comes from is that it's reduction, oxidation. So first 3 letters of reduction, first 2 letters of oxidation. And so essentially what a redox reaction is it is a reaction which is going to involve a transfer of electrons between 2 different species. So that being like 2 different molecules, 2 different elements, 2 different atoms. They have a supposed charge, and they are sharing electrons, transferring electrons between them in order to change that charge. And so hence we've got the reduction, which is a gain of electrons, and the oxidation, which is a loss of electrons. And so these redox reactions, they're very important. They're some of the most important reactions which we have, and they're occurring everywhere all the time, consistently occurring in your body. So for example, our bodies use redox reactions in cellular respiration, so converting sugar and oxygen into energy, water and carbon dioxide. Another example we have is that batteries, they rely on a redox reaction, and we'll go into that in a bit more depth later on, because that's quite an important concept in this topic, particularly when we think about things like galvanic cells and electrolytic cells, which are a type of battery. So oxidation states, or we can also call them oxidation numbers, are this number which we use, and we use it to keep track of how electrons are being shared within a molecule or atom. And it also helps us to then understand how the electrons are being transferred from a molecule or an atom to another molecule or atom. And so essentially this number represents the number of electrons that can either be gained, lost, or shared within a molecule. And there's a few rules which we need to cover in order to be able to then assign these oxidation states. So we'll go on to talk about those in a minute, and those are really important that you follow them in order, because they have quite a specific structure and are ordered in levels of their importance and priority. So you need to make sure that they're followed in order, and they are quite important to follow them in that order. And then also just throughout the slides, just to let you know, we're going to abbreviate oxidation state or oxidation number to either OS or ON, just to make that a little bit easier, just because to save writing the whole word. So just to clear that up so you don't get confused what that means. So these are our rules for the oxidation states. So rule number 1 states that any individual atom that is not combined with other elements is going to have an oxidation number of 0. So an example of that being, we've got oxygen, oxygen gas, which is O2. And so as long as that doesn't become combined with any other element, O2 will sorry, O2 will just become O2 with its oxidation number of 0. Similarly, if you just had magnesium and it was just like Mg, magnesium, it would also have its oxidation number being 0 because it's not combined with any other element. So you could also have something like ozone, which is O3, and as long as that's not combined with any other elements, it's just O3 because it's purely made of oxygen. O3 would then be considered to have an oxidation number of 0. Our second rule is that the sum of oxidation states of all of the atoms in a species will be equal to the net charge on that species. So there's a part A and a part B to this rule, and that's just because there's different ways which we can consider this for both a neutral species and for ions. So in a neutral species, the total sum of the oxidation state of all of the atoms is going to be 0. But that's the entire molecule will be 0. So, for example, if you have something like NaCl, sodium chloride, its entire because it doesn't have a charge on it, it's not an ion, it's going to have a sum of oxidation states of 0 in total. However, its individual atoms within that molecule are going to be charged. So its oxidation state is going to be 0, but that's because the sodium and the chloride are each going to have a value which then adds up to 0. So for example, the sodium is going to be +1 and the chlorine is going to have an oxidation state of -1, hence giving -1 + 1 gives 0. And so hence then you have the total oxidation state for the entire molecule being 0. And so that's important when you get the questions which ask you, you have sodium chloride, what is the oxidation state of sodium? And then you would know that, oh, it's going to be +1. For part B of this rule, we consider then ions, and so we have to consider that the total sum of the oxidation state is going to be the charge of the ion. So for example, the oxidation state of calcium 2+ is going to be +2. So you have Ca2+, and its oxidation state is +2. And so if we're then, that's just an individual ion in its own regard, so we don't need to consider anything else. We can just say that the oxidation state of the calcium in calcium 2+ is 2+. However, if we're considering an ion which has multiple different atoms in it and multiple different elements, the total sum of the oxidation states of all of those are going to add up to the charge of that particular ion. So, for example, if we're looking at the chromate ion, which is CrO4 2-, the entire chromate ion is going to have an oxidation state of -2, which means that everything in that needs to add up to -2. And so this is where it gets a little bit tricky, because you do have to apply some of the rules which we haven't looked at yet. We'll look at those next up. But basically, I'll give you a little bit of a preview into what they are, just to explain the chromate ion. But basically, each oxygen atom is going to have a charge of -2, which means that if you have 4 of them, that's going to be -8. And so if you have -8 from all the oxygens, that means you're going to need to add them up to -2. And so the only thing you then have left is the chromium. And so the chromium, you need to have the appropriate value such that you can get from -8 to -2. So you need to determine what's the difference between -8 and -2. That means that when you add the oxygen ion charges and the chromium ion charges, they add together to get -2. So if you've got -8 for the oxygen, you're then going to have +6 for the chromium, because -8 plus 6 is going to give you -2. So rule number 3 is that in a compound, the oxidation state will be based on the group in the periodic table. So for example, our group 1 metals, which are like sodium, are going to be 1+. If we're considering chlorine, that's down the other end, and that's in our group 15, and that's going to be a -1, because it's just based on those general ion rules when you're making an ionic compound. So for example, that's how you know when you have NaCl, chlorine is going to be -1 and sodium is going to be +1, because it's just following that general rule 3, as well as then combining that with the rule 2, which we have here. Rule number 4 is sort of just like an example type one which they give, because it still fits into the category of rule 3, but it's just very specified in order to sort of provide more context, I suppose. And so the oxidation state of fluorine is -1 in a compound. So when you have a compound that has fluorine in it, each fluorine is going to have an oxidation state of -1. Rule number 5 is that the oxidation state of hydrogen in a compound is going to be +1. And so that differs from rule 3, because rule 3 tells us that group 1 metals like sodium are going to have a +1 charge. And so hydrogen is not a group 1 metal. It exists in a gaseous state, and so that's why that's quite clearly specified for rule 5, because although it fits in group 1, it's not considered a group 1 metal, so it's kind of given its own little thing. Then rule 6 is that the oxidation state of oxygen is -2 when it's in a compound. And so obviously that's going to vary. If you've got something like O2, well obviously that's going to follow our first rule, which we have here, that the oxidation number is going to be 0, because remembering we follow the rules in their like chronological order. But the oxidation state of oxygen is -2 in a compound. So for example, combining rule 5 and rule 6, if we were to have water, which is H2O, the oxidation states of hydrogen, each one is going to be +1, and so because there's 2 of them, 2 times 1 is going to give us 2, and then the oxidation state of oxygen is going to be -2, so 2 minus 2 gives us 0, and because water is not charged, we can say that that then gives us an entire oxidation state for the water molecule of 0. Rule number 7 is that in 2-element compounds with metals, group 15, so 5A elements are going to have the oxidation state of -3. Group 16 or 6A elements are going to have an oxidation state of -2, and group 17, 7A elements, will have an oxidation state of -1. And so with this, it seems like there is a lot of rules, but many of them have quite a lot of overlap in them. So rule 3 is quite closely tied in with rule 7. Rule 4 also ties in quite closely with rule 3, and you could almost consider rule 5 to tie in quite closely with rule 3 as well. The only difference being that hydrogen's not a group 1 metal, it's just a group 1 element. So if we're to just look at this here, just to kind of get an understanding with rule 7, we can see that we've got like our group 17, they're going to be the 1- charge, then there's going to be like our 2- charge here, or -2 charge in group 16. Group 15 is going to be a -3 charge. This group here is quite variable, same with this one here, but typically this can be +4 or -4, but that will vary quite a bit. This one would be the +3, but that also varies quite a bit. This one here is +2, and this group here, group 1, is +1, as we spoke about before. And so we can see here these are our group 1 metals, which are fitting in with group 3, and then we've got hydrogen up the top here in group 1. Obviously not a metal, but still kind of following that general rule. So we're just going to go through a few examples of these. So our first one here is quite simple, and so the first thing we're going to do is look at rule number 1, because when we go back to rule number 1 tells us that any individual atom not combined with other elements will have an oxidation number of 0. And remembering our example was O2, that's purely made up of oxygen, no other elements in there. Despite it being 2 oxygen atoms, it's still only made up of oxygen. So our first example we've got is Cl2. It follows that same kind of general rule, and so we can say that any individual atom not combined with other elements has an oxidation number of 0. So we can see that this is going to apply here to this case, because chlorine isn't bound to any element other than itself. So each chlorine atom is going to have a charge of 0, and the overall Cl2 is going to have a charge of 0. Our next one which we have is NaH, sodium hydride, and so right off the bat in this case, we know that rule number 1, we don't need that because we've got 2 different types of elements in this one particular compound, and we can see that sodium is bound to a hydrogen, hence there's 2 different elements. So next we can look at rule 2, and so rule 2 tells us that the sum of the oxidation states of all of the atoms in a species is going to be equal to the net charge of that species. And so this rule does apply here, and this rule will basically apply all of the time. And so we know that the sum of the oxidation states for sodium and hydrogen is going to be equal to 0 because the compound is neutral. And so we might be inclined to jump ahead to rule number 5, where hydrogen has its oxidation state of +1. However, we do need to consider the rules in their proper order. So we've gone to rule 2. Next, we need to consider our rules in their specific order. So we remember that sodium actually has a charge of +1, and so hence hydrogen itself could not have a charge of +1 as well, because we know that the compound itself is going to be neutral and have a charge of 0. So if we had +1 and +1, we'd end up with an overall charge for sodium hydride of +2, and that wouldn't be correct in this circumstance. So we need to actually change the one which hydrogen is in this particular example. And so this is one where there is like hydrogen is going to differ from that rule, and that's because the sodium rule, where we're looking at the group 1 metals, is rule number 3, whereas our rule with hydrogen is rule number 5. And we remember that we do the rules in their specific order. So we would say that sodium is going to be +1, and so if sodium is +1 and we want the entire molecule to equal to 0 for its charge because the compound is neutral, we know that the sum of the oxidation states for sodium and hydrogen is going to have to add up to 0. So if we have +1, we have to do +1 with what is going to give us 0. So hydrogen is going to have to be -1. So we'd have +1 for the sodium and -1 for the hydrogen as the oxidation states. So we can say that the oxidation state for the entire molecule is going to be 0, but the oxidation state for sodium will be +1, and the oxidation state for hydrogen will be -1. Our next example that we've got is hydrogen carbonate, and so once again we're going to skip rule 1 straight away because we have a compound which has multiple different elements in it. So we immediately have crossed off rule number 1 there because it can't fit into that because we've got various different elements. So next up we've got rule number 2. And so with rule number 2, we can see that there is no charge overall, and so the sum of the oxidation states needs to be equal to 0. And so like anything which doesn't have a charge on it, the entire molecule is going to have an oxidation state of 0. And then in this case, we know that rule number 3 is not really going to apply because we don't have those kind of set out group 1 metals in there, or group 17 elements, so we can't apply that, and this is because it's mostly composed of hydrogen, carbon and oxygen. So rule number 3 is typically more useful for other elements, and so in this case we need to go on to our next rule, which is applicable, and that would be our hydrogen rule. So our hydrogen rule is telling us that hydrogen, we go back to our rules, we can see that hydrogen is going to be +1 in a compound, and oxygen is going to be -2 in a compound. So we can skip forward and we can say, well, hydrogen is each hydrogen is going to have a charge of +1. So we've got 2 of them, so it's going to be 2 times +1. So that gives us a charge of 2. So each hydrogen has a charge of +1. But overall, because there's 2 of them, we need to say that we've got +2. We know from rule 6 that oxygen has a charge of -2. So we can say -2 +2, that evens us out to 0 already. And so there's no charge overall in this entire compound. So if we've already got to 0 and we haven't actually factored in the carbon yet, that means we need to say that the carbon actually has an oxidation state of 0. So when we're considering this, the carbon's not really participating in the oxidation if this compound were to participate in an oxidation reaction. We'll look into that a bit further in a moment. But essentially, we can say that this entire molecule has an oxidation state of 0. Each hydrogen atom has an oxidation state of +1. Each carbon atom has an oxidation state of 0. And each oxygen atom has an oxidation state of -2. And so if we add those all up, we have +1, +1, +0, -2, and that gives us 0 overall. Our next example is looking at KMnO4, so that's potassium manganate. And so rule 2 tells us that the sum of the oxidation state should be 0, and again that's because potassium manganate does not have a charge, and so overall its oxidation state will be 0. We can then use rule 3, which tells us that potassium has an oxidation state of +1, because rule 3 tells us that our group 1 metals, such as potassium, have an oxidation state of +1. Rules 4 and 5 aren't going to apply because we've got no fluorine and no hydrogen in this particular molecule. And then so we next go on to rule 6, and rule 6 is going to tell us that oxygen has an oxidation state of -2. The thing we then need to note here is that we've got +1 for potassium, and then we're going on to oxygen, and we've got 4 oxygens. And so each oxygen, we need to remember, is going to be -2, but we've got 4 of them, so we've got to do 4 times -2. And so that gives us -8, but we're wanting to figure out what the oxidation state of manganese is. So we need to add up what we've got so far. So if we've got -2 times 4, that's going to give us -8. But then we've got to do -8 plus 1 because of the potassium. So we do -8 plus 1, and that gives us -7. So if our oxidation state without the manganese is -7, and we want to get it to 0, that tells us that the oxidation number of manganese is going to be +7. So if we go through the oxidation states for the entire molecule, the oxidation state for the molecule as a whole, for the entire potassium manganate, is going to be 0. The oxidation state for potassium is going to be +1. The oxidation state for the manganese is +7. And the oxidation state for each individual oxygen atom is -2. However, we have 4 of them, so all up there'll be -8, but when we're saying the oxidation state for the oxygen, we're saying that each one is separately and individually, so it's -2 for oxygen.